Now we'll move on to something called stability. Stability, as I wrote there, is a major focus in organic chemistry. Stability of different types of ions. See, I have put them in red, the things that we'll talk about this semester, in the first semester topics. We already started looking at the stability of various halogens, um, not halogens, uh, ions like CH3 minus, NH2 minus, OH minus, F minus. So we looked at those ions and how electronegativity helps us to predict which one is more stable. And we also then moved on from electronegativity to what we called negative inductive effect. So those two topics you will find in videos titled Electronegativity 2, 1 and 3. Okay. So now, since we are moving from electronegativity to a stability, have titled this stability, major focus. So we have already seen 1A, 1B under stability of anions. So there are other factors that explain the stability of anions. So there's something called resonance, which we briefly touched upon in the last video. The size of the ion that also matters, and then there's hybridization of the carbon, and there's something called aromaticity. So there are various ways, various factors which we invoke to explain the stability in different situations, in different scenarios. Okay, so that is stability of anions. We talked about 1A, 1B in previous videos. In this video, we'll focus on resonance, but we'll come to all these things in subsequent videos. Apart from stability of anions, we also have cations, and then we look at the stability of cations and how different factors explain the stability of cations. And then likewise we look at the stability of cyclic compounds, of alkenes. Within alkenes we can look at the stability of monoenes and dienes. So that's why stability is again a big umbrella which we need to learn and be able to apply the most apt criteria for any given situation. So with that introduction, we'll talk about how resonance explains the stability of different anions. Okay. So I need space. I'll get rid of all those things. So the first one, which I have my cheat sheet here, it's directly above the screen. So the first one is what we call an allyl anion. Okay, I'll draw that here. Maybe blue is better. So let's take this CH2 and a negative charge on that carbon. So if we want to draw this fully, this carbon here, I'll just call it carbon 1, 2, 3, 1, 2, 3. Okay. So carbon 1 is a CH2, carbon 2 is a CH. So there's a negative charge on carbon 3. Now, resonance, when we talk about resonance, there are certain rules. I'll mention a few of them now. So those electrons come in here and this electrons move there. So we get a resonance structure which is shown like this. So you see, this is something we have seen this before in another video in which we talked about the resonance in ozone, and that you had to go back a few videos and look under Lewis dot structures to see that example, ozone example. But these two structures together is the real structure of the allyl anion. This is the allyl the true structure of allyl anion is not this, not this, not this, but it's something in between. So the negative charge is not localized. So if you take an example, like for example, if you take OH minus, you see the negative charge is localized on the oxygen. If you take CH3 minus, the negative charge is localized on the carbon. But in this case, in the case of allyl anion, the negative charge is delocalized, is spread out. So whenever the negative charge is spread out, the ion becomes more stable. It's not in a hurry to react, it's stabilized, spread out over multiple atoms. So this is one example of resonance, and you see we are using something called a curved arrow to denote electron flow. Electrons are moving, okay, and the electron movement is shown by these curved arrows. These two electrons are forming a double bond between carbon 3 and carbon 2, and at that point, okay, I want to show that briefly. So in this picture right now, this electron, the negative charge, which means two electrons there on carbon 3, moved in to form a double bond between 3 and 2, and I have simultaneously showed that the double bond between 2 and 1 moved to carbon 1. So that is what this arrow represents. This double bond moved to carbon 1. So that double bond is no longer double bond, becomes single bond. Okay, so 1, 2, 3. Now I want to stop, like maybe it's not right, but I just want to show that to you, and then we talk about why it is not right. Okay? So now notice, you know that every carbon atom forms 4 bonds at most, right? It cannot form 5 bonds. It can form 3 with a positive charge, but the most carbon can form is 4 bonds. Now, see, look at this carbon right now. That carbon has a double bond, that's 2 bonds, a bond with hydrogen, which you can show it like that if you want to, and a bond with carbon. So this carbon, carbon 2, already has 4 bonds. Okay, so if you bring these electrons in when you are drawing the resonance structure, carbon 3 is bringing in those 2 electrons to form a double bond. So if we stop it there, look at this carbon. This carbon will have 5 bonds, 2 in a double bond there, 2 in a double bond there, and 1 with a single bond to the hydrogen. That's not possible. Carbon always forms 4 bonds at most. So for that reason, this double bond moves to that carbon. Okay, so you got this. Now you may ask, instead of moving the double bond, can I move the carbon hydrogen bond? Okay, I'll show that. So now you get why we are moving this, to satisfy the valence of carbon. Carbon needs to have 4. Now you can move double bonds, that's fine, but if we go to another point, let's just say here. Now I'm bringing the electrons here, and we need to move 1 bond to satisfy the valence of carbon, to keep it at 4. So you may ask, can I move this that way? So it's a hypothetical situation, so I'm showing you what will happen if that is so. You get this, but plus H minus. Okay. Now, whenever you draw resonance, there are rules, right? You cannot break single bond. You must not break single bonds. If you break a single bond, so cannot, must not break single bonds. Cannot break Because if you break them, it's no longer that compound. It's something else. It becomes something else. It's no longer the allyl anion. It's something else, completely different. Okay? So you cannot break single bonds. Okay? You can move lone pair. You can move electrons. You can move negative charges. When you are drawing resonance structures, what you can move negative charges, and that's because that's the electrons. Negative charge means 2 electrons there. You can move lone pairs. We'll see examples. For example, if there's oxygen in a molecule, oxygen will have like 2 lone pairs on it. So you can move lone pairs if necessary. You can move double bonds and triple bonds. You see, you moved a double bond here, and sometimes you may be able to, if the structure involves triple bonds, you can move one of the triple bonds. These are the things you can move. Okay? You cannot break single bonds. You must keep the maximum valency of every element. So carbon forms 4 bonds at most, right? So we cannot draw a structure in which carbon has 5 bonds. Okay? Nor can you break single bonds. So keep all these rules in one place. Maybe what you should do is, after you listen to every video, just come up with like a 2 or 3 line summary of each video. And you can always go back and check, go back to the summary and see if you got everything out of the video. Now, so this is allyl anion. There's one resonance structure. So now I'll erase this and look at another example. And the name of that compound is diazomethane. Diazomethane. And the structure is like this: CH2, double bond N, double bond N. Okay. Now, this one has a negative charge, and you see this nitrogen has 4 bonds, so this one will have a positive charge. Now, can we draw a resonance structure to this? Yes, you can draw a resonance structure to this. You move the negative charge, that way, and then the nitrogen can form 4 bonds at most, and this nitrogen in the center, this nitrogen already has 4 bonds, so it cannot accept a new bond with this nitrogen and keep the other 2, then it will have 5, so it moves the double bond to this carbon. So we get CH2, negative charge on the CH2. Okay. Now see, this nitrogen has positive charge because it has 4 bonds. So this nitrogen will still have positive charge. And that brings up another rule of resonance. Okay? So that rule is all the possible resonance structures that we draw, here there are 2 of them, the original one and then this one, must have the same charge, total charge. Okay? The total charge in this structure is 0. There's one positive charge and one negative charge. The total charge is conserved, it's maintained 0. Maybe in another, in a different compound, you can maybe say you started with 1 plus and 1 minus, maybe you come up with 2 plus and 2 minus, but the total charge is 0, it's conserved. So that's another thing we must keep in mind. So again, make rules of resonance, right? So again, you see, the octet rule is satisfied everywhere. The nitrogen has an octet there, that nitrogen has 8 electrons, this nitrogen has 8 electrons, this carbon has 8 electrons, same thing this. And again, just so you know, for practice, you can look at the loose dot structures of this and maybe calculate how you got that negative charge there, a positive charge there, no formal charge, which goes back to our loose dot structures discussion. So we have looked at 2 examples of resonance of anions. will stop here.